Hello, my name is Paul Traylor, and today I'm going to be presenting about using Prometheus to provide large-scale monitoring for your organization. So to start with, I just want to give sort of a brief introduction of myself. So I grew up near Raleigh, North Carolina, in a very rural area. Now, when I talk with my Japanese friends and say rural, they think one konbini and maybe one bus stop. But for me growing up, no konbini, no bus stop, very rural. Then after graduation, I went to San Francisco, where I worked at 2 different startups. And I sort of picked up Japanese as a hobby. I thought it would be kind of a fun personal challenge and enjoyed studying, practicing with my friends. And after a while, I wanted to try living in Japan. And so after coming over as a student, I really enjoyed Fukuoka. Very nice urban environment, but also very close to nature. And I wanted to stick around longer. And that's how I came to Line Fukuoka, where I've been for the past 4 years. Now at Line Fukuoka, I'm primarily focused on monitoring as a service, but sometimes as a hobby, I will dabble in Swift and iOS development a little bit. So for today's agenda, I want to start with kind of a basic overview of Prometheus. And then I want to talk about how we use Promgen to manage Prometheus at Line. I want to speak a little bit about some rules and alerts and how to route them. I want to talk a little bit about supporting multiple tenants. And then lastly, I sort of want to cover taking your Prometheus setup and scaling that for long-term metrics. So to start off with, well, what is Prometheus? So Prometheus is a pull-based monitoring system. But what do I mean by pull-based? So for example, other monitoring systems like StatsD or Graphite, your server will push data to the monitoring server. Now this works, but sometimes it can be very easy to accidentally launch a denial of service attack against your own monitoring system. You also have to be careful because it's difficult to tell if your service is up or down because you can only look at the absence of data. However, in the case of Prometheus, it's a pull-based system. So it's much easier to schedule your monitoring scrapes, and you can kind of avoid DOSing your monitoring server. It's also much easier to know if your node is up or down because your Prometheus server has a list of all of the targets that it's monitoring. And so it's very easy to know if this node fails its scrape. Prometheus also has very flexible alerting rules. So previously, you could only really set a single threshold, warn me if this hits a threshold. But with Prometheus, you can actually write promql and write very complicated, very detailed alerts for many different situations. Prometheus is also supported by default in Grafana, which means a lot of people are already using Grafana and already have that support by default. Prometheus is also one of the Cloud Native Computing Foundation projects. It was one of the first external projects to join. It was also one of the first to graduate and hit all the criteria for graduating to show sort of a well-run project. Currently, it is undergoing a standardization process under open metrics. And what this means is that a lot of different services that support this open metrics format will sort of automatically be able to be monitored by Prometheus by default. So quite useful to have this built in. So then what is Promgen? So Promgen is a tool to provide Prometheus configuration via file discovery. It also will route your notifications from Alert Manager to different endpoints, maybe email or chat or additional webhooks. So why did we build Promgen? So first off, as developers, we don't really want to write manual configurations. It's kind of annoying. We don't really want to write a Prometheus scrape config. You don't really want to manually write a bunch of these rules. And we don't really want to write routing rules for all of our methods. As a developer, we really want a web UI so that it makes it very easy to configure our notifications and targets. So Prometheus itself has a lot of discovery methods built in, so a lot of ways to find its targets. And this could be Kubernetes, it could be console, it could be Docker. There's many supported discovery methods. But for anything custom, typically you do via file discovery. So you have the Promgen web UI, where you input your targets and your monitoring settings. And then there's a Celery node on each of your Prometheus instances. So when you edit in the UI, it will push the updates to your Prometheus nodes and then update the file and reload. So now I sort of want to talk about Prometheus at Line. And so at a company like Line has sort of a very, very big scale. And what do I mean by that? So our current cluster that my team is managing is one of the larger ones within Line. And right now we are scraping about 46 million time series. And we're doing that on about a 15-second interval, our scrape interval. We're also monitoring about 34,000 different targets. And that could be directly instrumented applications. It could be middleware via different exporters. It could be any number of things. Because we're monitoring so many different targets, we have it sort of divided up into multiple shards, have about 9 or so different shards that we've broken it up to. And depending on how busy a particular shard is, a single Prometheus server could be monitoring between 2 million up to 8 million time series all at once. And depending on that volume of data, it could be from, at the low end, only 2 weeks of monitoring data, 2 weeks of retention, to more than maybe 10 weeks on a less loaded server. So sometimes there's a pretty big range depending on what is being monitored. And again, at a company like Line, we're working on a fairly large scale. So we have to worry a lot about reliability, both our normal day-to-day load, but also maybe spikes in load. We need to sort of understand how things are routed and be able to get our performance metrics and alert on those. We're also working with many different teams, many different groups, so we have to worry about multi-tenancy. Lastly, since we sort of want to store our monitoring data for a very long time, we also sort of have to worry about, well, how do we reliably store data for long periods of time? So sort of going into our Prometheus environment a little bit, we have it broken up into a couple of different clusters. So at the top, we have sort of our alpha testing environment. This is where we do sort of basic integration tests and test how all the components sort of work together. And here we pretty much run mostly on VMs because we don't really care about load testing as much as sort of the integration testing. The next step up from that is our beta cluster. So this is where we do a little bit more serious integration test, but also some load testing. This is also where our developers, when they're building their service, their development and staging versions, this is where they can register their development versions to monitor. However, since this is kind of a testing environment in many ways, we do typically turn off many of our default rules, like our exporter up metrics and a few others, because in a development environment, a lot of our services go up and down very frequently, so we kind of want to avoid that noise. Lastly, we have sort of our main release cluster, and this is where we're monitoring all of the live services. So these are any of the services that are handling live traffic, working with our real users. So sort of digging into our release cluster a little bit. So currently we're running our release cluster on about 20 Prometheus servers. And all of these are typically physical servers. They have about 20 CPU, 256 memory, 10 gig network, and about 2 terabytes of space. For reliability purpose, for high availability purposes, typically we're always running pairs of every Prometheus server. So 2 Prometheus servers per shard. So one of the reasons that we use physical servers as opposed to virtual servers is because when you're running Prometheus at this scale, having a lot of memory and a lot of disk space is typically very useful. We could technically run these on virtual machines, but if we're making a very big virtual machine, then typically that's going to use most of the hypervisor by itself. And so we don't really get a lot of usefulness out of a hypervisor. It's mostly just overhead. So after that, we have kind of our web service, our web tier. And this is sort of handling the dashboards, the Promgen UI. So we have Nginx, Grafana, Promgen, and the Thanos query component, which we'll cover a little bit later. But these are our web server and mostly stateless. So we could easily scale it to 3, 4, or more nodes if we needed to. Lastly, we have a couple of other specialized nodes for this black box exporter probe. So normally with Prometheus, Prometheus is directly monitoring the target, directly getting a number of metrics. But in the case of black box monitoring, typically you want to look at things like the HTTP status code or your SSL certificate expiration. So you need something to sort of proxy that request to get those stats. Again, we tend to run everything in pairs, but in this case, we have one pair running inside of Verda, our private cloud, to monitor internal API calls and so on. But we also have 2 nodes running externally in AWS. And this is nice because we can monitor things from the outside almost the same way any of our users would be interacting with those APIs from externally. So in addition to sort of the physical server sharding, we typically have things broken up on kind of a role. So for example, in our current environment, we have kind of 4 general purpose shards. And what I mean by general purpose shard is that any developer within line that needs to monitor their service can quickly load up the Promgen dashboard and register their targets and their exporters and anything that they want to monitor. And so this is sort of free for everyone. However, there's also many use cases where teams have very specific needs, or need something a little bit more custom. So to go through a couple of examples, so our first example is Line Shop. Now the Line Shop team has quite a large number of services, usually running a combination of Spring Boot and Armaria and that kind of thing. So in the case of Line Shop, they typically don't have a large number of targets, not too many different instances deployed, but each instance tends to have a very large number of samples, a large number of series. And this is mostly because in Line Shop, there's many different internal API calls, and there's a lot of different URL routes that we're tracking. And so Shop has its own usage pattern, and that's why it has its own shard. To contrast that, our data analysis teams tend to run things like Hadoop and Fluentd and other cluster services. In this case, each individual target maybe doesn't have as many metrics. However, there's usually a larger number of targets. Because if you're running a Hadoop cluster, you typically have many, many, many Hadoop nodes. To further contrast that, our ads platform team looks even different. So in the ad platforms team's case, they're running many, many microservices, typically in Go. But as they're building these services and running their campaigns, they kind of have a tendency to add a lot of campaign IDs into the Prometheus labels. So in this case, you have to be a little bit careful because you can hit large cardinality problems. Your number of metrics can grow to a very large amount. Lastly, sort of to contrast even those, we have our securities team. And anytime you're working with something like securities or money, you want to be very careful because there tends to be a lot stricter. So in the case of a team like securities, we actually run a completely separate cluster, completely separate Prometheus and Promgen instances just to keep things separate and secure. And so now that we have our Prometheus servers running and collecting a lot of data, we also have to worry about alerts. When things go wrong, where do we route them? And as you can see, the alerts can sometimes spike and be all over the place. So within Promgen, we typically use 2 labels, service and project, to route notifications. Now within Promgen, a service would be something like line shop or line vital, and a project could be something smaller like line shop API or line vital admin panel. But when you're writing these rules, and if you're not used to promql, it can be really easy to accidentally erase your labels using the aggregations like sum or count. And so what this looks like is if I take the sum of some metric, I will usually get a single value back. But if I only have that single value, I have nothing to route. Promgen doesn't know who to send the message to. So in this case, what I might do is sum by service and project. And now I have my service and project labels that I can route on. Of course, I don't have to use an aggregation. If I just query a metric by itself, it will return all of the labels. And of course, Promgen can route on service and project. So there's no real issue. And so because we're providing this monitoring, there's certain things that we know developers want by default. We kind of want to know things like how much memory is our service using, how much disk is available. There's certain things that almost all projects need. Of course, each team is also free to customize their rules and add custom rules. Each service may have specific metrics that they care about or specific things they want to alert on. And so that's supported. However, it is kind of difficult to set a single default that everyone can use equally. So in that case, what we do is we provide support to override those custom thresholds, to override those custom rules. And so what this looks like is within Promgen, we have what we call an exclude tag. And this is used so that you can have a parent rule, but exclude the child rules. And so what this looks like is if I have an example rule with my exclude tag, it will expand into this tree that you see below. So there might be an example rule at the parent that is everything except service A and B. So then under that, we have maybe our service A rule, which is looking at its specific threshold. Under that, maybe we have our service B rule that is looking at a threshold. However, under service B, maybe we also exclude our project because maybe we want to have a project-specific override even under our service override. And this is something that Promgen supports. And another thing, since we're sort of running this at a global kind of for all teams, there's also kind of global metrics that we sort of want to help see. So for example, a lot of times we want to know sort of how many samples are being scraped, and we want to sum it by service, project, and job to get sort of an overall view into how things are running. So at the start, we write a recording rule so that we can get our meta samples sum measure. Now, because we want to see if our load is increasing and see for capacity planning, what we can do is take our current meta sample sum, and if it's twice what it was 1 week ago, we kind of want to know about it. Maybe a service has an error and is suddenly more popular. There's many reasons we might want to know about it. We do, however, put one more restriction on it. We arbitrarily set it at about 100,000 metrics, because if a small service doubles, from a monitoring perspective, we don't care too much. But if a very large service doubles, then suddenly we may have an issue. If a project suddenly is scraping an additional 1 million metrics, it could be an issue. And so because of that, we also have a scrape samples alert. So if a single scrape hits 100,000 metrics, then we probably want to take a look at that. And so that's another of the global rules that we have set. Lastly, because we have to worry about SSL certificates everywhere, we often set other global rules like this so that developers can be reminded when it's time to renew their certificates. So furthermore, since we're running this as a service, we also sort of want to know how our Prometheus servers are doing. So because alerts are very important for an alerting system, we tend to check the rate of both the alert manager notifications failed, but also the Prometheus notifications failed, because we want to know how well is it doing. But typically these we monitor from a different Prometheus server in a different data center to make sure that even if our existing cluster goes down, we still have our meta monitoring. Lastly, because we're running most of our Prometheus servers in pairs for HA reasons, we want to make sure that their configuration is also in sync. So for example, we can take the max timestamp by the min timestamp and check the difference between those to make sure that our servers are properly in sync. So now we sort of have to start thinking about what our multiple tenants, because we have many different people using our monitoring system, and it's shared across many different teams. So in our current largest Grafana instance, we have about 400 active users, and this would be active users over the past month. And in this instance, we have divided up into maybe about 50 different organizations or 50 different teams using this instance. And across these orgs and users, we have about 1,300 dashboards to look at different metrics that different users have created. Now, sort of with our Grafana tenants, we have sort of our shared instance that I mentioned earlier. And this has kind of basic group permissions for anyone within line. For this instance, typically we auth against our internal GitHub Enterprise instance. So any developer that has access to GitHub also has access to metrics to view. In addition to that, for any of our project managers or other teams that maybe don't have code access but still want to look at metrics, we can always manually add them to the Grafana instance, and we do that fairly often. So then for many teams sometimes want more custom dashboards or maybe customize more of their data sources. So we also often create team-specific organizations within the Grafana instance. And then in this case, that team has free reign to add as many dashboards or edit dashboards or add any other data sources that they want. But within Line, we have many different people working in many different teams in many different areas. So we also have many contractors that are helping us develop services. And so in this case, we actually have even more Grafana instances, this time targeted at some of our contractors. So in this case, we actually have separate Grafana instances running in Docker containers. And we have it set this way because typically, if we want to auth against a specific GitHub org, then typically Grafana can only auth against a single GitHub organization. So each contractor organization, each contractor instance is auth against a specific GitHub org. Furthermore, because these are contractors, we want to be a little bit more careful, and we want to make sure that these contractors can only see the data that they're responsible for. So we have to worry about security a little bit more. So to sort of handle this, we have a tool that we call promql-guard. And what promql-guard does is it sits between your Grafana instance and your upstream Prometheus instance. And it implements the same API as your upstream instances. So from Grafana's perspective, it's just talking to a normal Prometheus instance. And promql-guard will look at your query, it will rewrite your query, and make sure that it's safe to pass to the upstream instance. So for example, what we might have is a HTTP password list of all of the tenants that we want to allow. And this is the same as Nginx or Apache. It's the same HTTP password format. So then under that, we might configure multiple tenants, tenant A, tenant B. And for each tenant, we might set a certain Prometheus upstream instance, but also the Prometheus matchers that we want to restrict to. So then when you're running a query like this, if the user sends the query foo minus bar, then promql-guard will look at that query, rewrite it, and then send it up to the parent or the upstream instance. So your foo minus bar is rewritten to be foo service tenant A minus bar service tenant A. And so then when that's passed up to the Prometheus server, it will only return the metrics that it's supposed to. So in the case of querying for the secrets for app X, so our query again will be rewritten by promql-guard to be secret app X or app is app Y and app Z. So in this case, you can see that it can't be both app X and app Y or X, app Z. And so in this case, when that gets sent to the upstream Prometheus server, then the upstream Prometheus server will not be able to return anything and will be fine. They can't see data that they shouldn't. And so in Line's case, again, we have Prometheus that does a very good job showing recent metrics data. Prometheus is very well optimized for that. It's fairly efficient. It stores things local to disk so that nothing's kind of shared, and it's fairly reliable. However, there's very often cases where we want to know what happened 6 months ago or maybe a year ago. For example, in Line's case, every year we typically need to scale up for New Year's. So every year on January 1st, everywhere around Japan, Akeomet, and we typically need to deal with scaling for that. So we also really want to know what happened last year in January. And so since Prometheus is only really focused on recent data, we sort of have to look at other options for how we store and access this historical data. So what we've been using recently is a tool called Thanos. And what Thanos does is it adds long-term storage on top of Prometheus. So Grafana is same as usual, and Grafana will now talk to our Thanos query API. Now, Thanos query API will have the same API, it exposes the same API as Prometheus. So from Grafana's perspective, it doesn't know any different. Within Thanos query, it will now use the internal thanos-store API, which in this case is implemented by both Sidecar and thanos-store. So Thanos Sidecar will take these queries and talk to Prometheus over the remote read API. And so it can take the Thanos query and query from Prometheus, return the data back. In the case of thanos-store, it will take that same query, but in this time we'll pull it from object storage. It will pull the cache down, run the query, and return the data. Now, Thanos Sidecar has one additional role in that it will periodically take the Prometheus blocks that are written every couple of hours and will upload that to object storage. Lastly, this Thanos compactor component will periodically take data from object storage, pull it down, compress it, and then upload it back. And this is kind of an optimization step to sort of make it run a little bit better. And so Thanos internally uses a data model where it uses object storage to hold your long-term storage data, holds your data. And in our case, we're currently storing about 150 terabytes in object storage right now. And we're storing about 600,000 objects. So quite a lot of objects and quite a lot of data. And right now we're targeting we have about a year's worth of data in our release environment, but actually almost 2 years in our beta environment. And we're trying to continuously work and optimize this to, as much as possible, keep data forever. Also, sort of Thanos doesn't try to reinvent a new format. It typically uses the Prometheus block format as is. And these blocks might be 2-hour blocks, 8-hour blocks, 2-day, or 2-week. However, in our case, because we're processing so many metrics, because we have such a large metrics load, some of our 2-week blocks end up being about 500 gigabytes, which leads to a problem I'll cover in a little bit. So in terms of scaling Thanos, the two things that we typically have to scale the most are the compact nodes and the store nodes. In the case of the compact nodes, typically we need a lot of disk space to rewrite these blocks. And like I mentioned, some of our 2-week blocks are already about 500 gig. So typically we have to download many blocks, write out a new block, and upload it again. So because we have very specific disk requirements, sometimes we even have to kind of ask our Verda team for custom nodes of a certain size. Also, we have to sort of scale the Thanos store nodes. And in this case, we need both disk and memory. We need disk to cache the blocks when we download it from object storage and cache it locally. We also need a good amount of memory for our Prometheus index. So when we're looking up a metric, we sort of need that index to just be stored in memory. So when scaling our thanos-store node, we can sort of scale it on two different dimensions. So on one dimension is just our basic time dimension, which we can use our min time and max time flags. So for example, we could have one store node showing the past 4 weeks, and then the next one the next 4 weeks, and then the next 4 weeks. And so time is a very natural dimension to scale on. But sometimes even just time alone becomes a little bit difficult to scale on just by itself. So in that case, we could also probably scale on labels. And this label could be our different replica label from earlier, for example, our line shop team or our data platform team, or any other kind of label dimension that we want to scale on. So we sort of have both of those options. Also, the relabel config is the same relabel config as the Prometheus one. So most of those rules can be reused with no problem. So then sort of the next part we have to scale is, again, our thanos-compact nodes. And again, like we have our same relabel config, so we can scale it on different label dimensions. But again, sometimes we have a very tight disk restriction because it's sometimes difficult to get a custom node for the amount of disk space that we need. So in this case, we're actually using our debug max compactions level. And so for some of our nodes, we only compact it up to the 2-day nodes, just because we don't always have enough disk space to work with. But again, with the Thanos compactor, if you only have one compactor pointed at one bucket, you have kind of a very bad serial problem where it will keep going in serial trying to go through all of your data and eventually gets very far behind. So often you want to use your relabel config and sort of change this into a parallel one where we have a compact node for each of our sort of logical shards or groups. So sort of to tie it all together and sort of summarize most of our thing, so Prometheus itself can scale actually very, very well. The Prometheus on-disk format works very well. A single server with enough memory and disk can process both a very large number of metrics, but can also keep a retention for a decent amount of time. Of course, as your tenants increases and as sort of the number of metrics that you're targeting increases, then you can sort of start sharding your Prometheus and put a subset of your targets on different Prometheus instances. And this will get you much further, being able to scale just with Prometheus alone. Now, you do have to be a little bit careful with writing your rule queries because you need to make sure that your query gets routed to the correct team. You don't want to lose labels that you thought you had. You want to make sure that the developer gets the alerts that they wanted. You also have to sometimes be careful with performance of queries. When you start supporting many different tenants, you also, again, need to be very aware of how you're sharing data. You need to make sure that Team A can't see Team B's data unless that's something you specifically allow. And maybe you handle that, again, with separate Grafana instances and dashboards, or maybe you use something like promql-guard to look at your queries and sort of check to make sure that those queries should be allowed. Lastly, again, Prometheus works very well for short-term recent data, but if you need to scale that further, then you can take advantage of tools like Thanos. So again, Thanos will basically, from most tools, from Grafana's perspective, look the same as any other Prometheus setup. However, by using a combination of the Thanos sidecar and the thanos-store nodes, you can suddenly scale up using object storage, and suddenly, instead of going from a couple of weeks data, you can then sort of scale up and see many years data or however much data you want to retain. You just have to be a little bit aware of what resources you're using and how you're scaling your compactor nodes and your storage nodes. Well, that's the end of my talk today, but I hope you enjoyed it, and I hope you can enjoy many of the rest of our talks. Thank you very much.